Hello, good morning, good afternoon, good evening to everybody who's watching this. Thank you so much for taking the time to listen to my presentation. This is the presentation for the I2CACIS2021 conference in Malaysia. I want to express my deepest gratitude to the organizers of I2CACIS 2021 for for organizing this conference under the circumstances. It is a pleasure and an honor to participate in the conference again this year. My role today is to present my paper, which I have submitted for consideration to this conference. The title of the paper is Nonlinear Analytical Mathematical Modelling of a Hybrid Fixed-Wing Unmanned Aerial Vehicle in Pusher Configuration. My name is Zairil, Zairil Ashar bin Zaludin. I'm from Department of Aerospace Engineering in UPM. I've been an academic staff for a while now. My area of specialty is automatic flight control systems. I have a deep interest in unmanned aerial vehicles and anything that flies, basically. The background image that you see in the slide right now is the place where I often fly my prototypes. So this is a place called Ladang Puchong in UPM Serdang. Exactly, the location of the place is in Puchong. If you are keen to watch us do some flight testing, or you want to do your own flight testing in our place, do get in touch. Without further ado, let's go straight into the paper. I put up here some pages of the article for everybody to see. It's a full conference proceeding, and I think each one of us will have a copy of this sent to us by the organizers. What I intend to do in this particular video is to go through the paper a little bit, basically to explain what we have done to prepare these results and then share with the audience. So this is the brief program I have for this video. I will begin with an introduction to the problem. Then I will talk about the problem statement, what exactly that we are working towards to, the objective of the work that we have done, the methodology that we use, the results, conclusions, and finally the contribution that we are making to the UAV community and also the control systems community. This is the picture of the runway that we are using to take off and land our fixed-wing UAVs. The reason why I use this picture is to illustrate the problem that we are currently facing, or the industry is currently facing, with unmanned aerial vehicles and drones. Usually people use fixed-wing UAVs when they want to fly long hours or they want to carry heavy payloads. Fixed-wing UAVs have been said to be able to do longer duration flight. That's not strictly true. The secret that makes fixed-wing UAV able to fly longer is not in its configuration, but it is in the propulsion system that it uses. So fixed-wing UAVs that can fly longer than usual are usually powered by internal combustion engine. So if you use a fixed-wing UAV that is powered by battery, most likely you are still going to fly around 30 minutes maximum, and you are probably not going to be able to carry that much payloads compared to fixed-wing UAVs that are currently flying using for example, petrol engine or heavy fuel engine. Okay, so this is the limitation of fixed wing UAV basically. The UAV needs to fly, needs to take off and land with the help of a runway. um, and if you can do that, then the UAV can fly with all the perks that fixed wing UAVs have to give. Rotary wing drones, rotary wing UAVs have a limitation as well. Their limitation is they can fly, between 15 to 30 minutes, and they cannot carry that much payload compared to the fixed wing UAVs. So among the community of UAV experts, if you will, and enthusiasts, and those who are involved in the industry, they thought what would be great is to come up with a hybrid solution. So best of both worlds. So a mix of fixed wing as well as rotary wing. In short, what they are hoping is to come up with a fixed wing aircraft that is capable of flying long hours and carry heavy payloads, but capable of vertical takeoff and landing at the same time. Hence, they call it the hybrid solution. So let's look at the problem a little bit deeper. So you have the fixed wing UAV examples on the left hand side here. Then on the right hand side, you have the rotary wing UAVs, aka drones. Then you have the ones that are so-called hybrid that are currently flying today. So the ones today, the limitations that are currently flying, most of them are still battery operated and rather small. They are capable of doing a lot of good things in lab, and not in the industry as what the industry wants. So the best solution still is to insist on using the right propulsion system for the fixed wing aircraft, as well as the VTOL motors to enable the aircraft to fly vertically upwards and also to land the aircraft in a vertical way. Okay, so I summarized it in this slide, what we have just mentioned just now. So that's pretty much, setting up the work that we have done. We are trying to solve this problem by firstly introducing, a complete 6 degrees of freedom equations of motions for these aircraft. Okay. So on the hardware side, let's have a look. This is another example of the fixed wing UAV that we have in UPM. You can see that at the back here you have the engine, the main propulsion system. So the configuration of this particular aircraft is what we call the pusher configuration. It's a petrol engine with a 60cc size. It's an inverted V-tail, capable of flying long endurance as well as carry heavy payload. Okay, so what we intend to do is to use this as a platform to analyze this hybrid capability of this particular UAV. So if we were to actually incorporate the VTOL motors, this is probably how it would look like. Okay, so you have on the left hand side without the motors, and then on the right hand side you can see the motors are arranged in an H configuration. Right, so if we were to get rid of the photos and then just focus on the schematics, this is how it will look like. So from the top view, you have the main propulsion system acting as a pusher, and then you have the 4 rotors acting as the VTOL motors. On the right hand side here, the image shows the direction of motion of the aircraft as a result of this propulsion system. Right, so the next thing that the person who's going to derive these equations of motion will have to do is to introduce the variables that are involved in the derivation. So this is quite extensively explained in the paper that we are publishing. So we use the conventional symbols in aerospace engineering to mark the angles as well as the velocities involved. We are also making assumptions, and those assumptions are stated in the paper as well. So in addition to all those, we are clearly indicating the forces and the moments involved in the motion of this particular aircraft. We are also indicating the distance where these forces and moments are acting with respect to the center of gravity of the plane. Right. So the paper clearly states and indicate the direction of forces and the moments. So we went through and we went through the process of elaborating, if you will, Newton's second law. We start with Newton's second law and then slowly develop the equations of motion step by step. We produce the response forces, the response moments of the aircrafts, and by doing so, step by step, we managed to obtain the three equations of forces and then the three equations of moments that represents the 6 degrees of freedom equations of motion for this hybrid plane, or hybrid fixed-wing unmanned aerial vehicle in pusher configuration. So one can see that the contributions of the engine, the main engine, is visible in this equation of motion, and also the contribution of the rotors that provide the vertical lift is also present along with their distances from where the forces and the moments act to the center of gravity. So that's the whole purpose of this paper, which is to produce this non-linear mathematical model of this hybrid plane. So to conclude, we have completed the derivation of 6 degrees of freedom equations of motion for this range of hybrid unmanned aerial vehicle. Using these equations, the influence of VTOL motor locations to forces and moments can be analyzed much better. And they really appear in the equations. So these equations will act as the platform for us to develop suitable automatic flight control systems and also to study the dynamic behavior of this particular aircraft when subjected to disturbances and control inputs. So those are the conclusions that we are making. Okay, so that's pretty much the contribution that we are hoping that we can make to the community. We created the 6 degrees of, we have derived the 6 degrees of freedom equations of motion for this type of hybrid aircraft, and this act as a basis for the further work that we are going to do on this particular plane, which will include the design of the automatic flight control systems for this plane. Okay, so that's all from me. Thank you so much for listening to my presentation. Do come and visit us one day, and if you are free, please come and visit our websites. You can see the address of the websites here, and I would like to express my gratitude and my thanks to the organizers of I2CACIS 2021 again. Sincerely, I do hope that we can meet again and then do a face-to-face conference very, very soon. Okay, so that's all from me. Thank you so much. I hope to see you again very soon. Thank you.